In this video, I'm going to talk about photoelectric effect. Let's take a metal, any metal. Yeah. This is a metallic surface. Let's expose this metal to an electromagnetic radiation, let's say red light. The frequency of red light comes in the visible range, which is a part of electromagnetic spectrum, so red light. You're shining this red light onto this metallic surface, and you notice that some electrons are jumping out of this metallic surface. So these are electrons, they are coming out of this metal, so electrons. This effect is called photoelectric effect. So how do we define photoelectric effect? I'll write the definition for it. The emission of photons from a metallic surface when exposed to an electromagnetic radiation is called the photoelectric effect. Okay, now we have a lot of questions. Why does it happen? Does it happen every time? Does it happen with any electromagnetic source? Does it happen with every metal? Let's try to answer these questions. So let's start with why. Why does it happen? According to Max Planck, electromagnetic radiation is absorbed or emitted in the form of packets of energy called quanta. For example, if you have an infrared source, IR source, it emits infrared radiation. This radiation is not continuous, it's discrete, just like this, as packets of energy. For a light source, we call it photon. So how do you find the energy of a photon? It's HF. That means this photon has an energy of HF, this photon has an energy of HF, this photon has an energy of HF, 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 HF. So what's the total energy emitted by this IR source? We have 10 packets of energy, 10 photons. Each photon has energy HF. So the total energy emitted by this infrared source is 6 HF. Okay, but what is H and F? H is a constant called Planck's constant. So Planck's constant has a value of 6.634 times 10 to the power of minus 34 joules per hertz. That's the constant. Now F is the frequency of the radiation. Let's consider another example. So we have a source that emits green light. So this is a green light source. Let's say it has emitted 10 photons. So each photon has an energy of HF. So this photon has an energy of HF, this photon has an energy of HF. So what's the total energy emitted by this source? 10 HF, right? Now if you know the value of frequency, you can substitute it here and find the total energy. These light sources emit radiation by vibrating its atoms. So how do you write the energy of vibration, the general equation for energy of vibration? Energy of vibration is equal to NHF, where N is a whole number, 0, 1, 2, 3, etc. H is Planck's constant, and F is the frequency of vibration. Let's talk about this N. N can take only whole number values. It cannot take any fractions. So energy can be absorbed or emitted as the whole number multiples of HF only. For example, a source can emit 3 HF or 5 HF or 100 HF or 1 million HF. It's totally fine. But it cannot emit 2.5 HF or 3 by 2 HF or 100 by 3 HF. This is not possible. Makes sense, right? Let's say you're going to market to buy 10 pens. Okay, you can buy 10 pens or 15 pens or 20 pens, but you cannot buy 2.5 pens or 3.8 pens or 3 by 2 pens. Yeah, this is very similar. Now, let's talk about the energy levels of an atom in a metal. Um, there are a lot of energy levels. So let's say this is the ground state energy level. It has the lowest energy. This is the outermost shell, so it has the highest energy. Outermost shell. Let's say the energy difference between these two levels is 5 electron volt, just a random number. The energy difference between these two energy levels, let's say 3 electron volt. The energy difference between these two energy levels, let's say 2 electron volt. Energy difference between these two, 1 electron volt. So these are the energy levels of an atom in a metal. Let's consider an electron that is initially at the lowest energy state, in the ground state. So that's our electron. I have a visible light source here. So that's a light source, visible light source. So it can emit electromagnetic radiation in the form of packets of energy. So let's say this visible light source is emitting red light. So we have a red photon here. And let's say the energy of this photon is 5 electron volt. Okay, that's the energy of this photon. Again, a random number, not accurate. 5 electron volt. So what would happen? This photon interacts with this electron. It transfers the energy to the electron. So the electron absorbs that energy. It cannot stay in the ground state anymore. It absorbed 5 electron volt, right? So it would jump to the 5 electron volt energy level. The electron is now here in the first energy level. I'm increasing the frequency. Okay, by increasing the frequency, you can increase the energy of the photon. So let's go back. So now this light source is emitting green light. So that's a photon. So green photon. It has an energy of let's say 8 electron volt. So the same thing would happen. It would interact with the electron, transfers the energy to the electron. Electron absorbs the photon. Then it would jump to the energy level with an energy value of 8 electron volt. So it would jump to the second energy level. Because this is 5, this is 3, so the total is what? 8 electron volt, right? So this electron would jump to the second energy level. Our electron is here now. Okay, let's go back. Now let's say this visible light source is emitting a photon with energy of 4 electron volt. Okay, this photon would try to interact with this electron. It would try to transfer the energy to the electron. The electron would try to absorb that energy and would try to jump to the energy level with energy 4 electron volt. But there is no such energy level. There is no energy level with energy 4 electron volt. So this electron cannot absorb that photon. Yeah, so nothing will happen. The electron will not jump. Now let's go back. This time I'm adjusting the frequency and I'm emitting blue light. So this is a photon with energy 11 electron volt. So what will happen? It will interact with the electron. It will transfer the energy to the electron. Electron absorbs that energy. It will jump to the energy level with energy 11 electron volt. Okay, so let's see if there is such an energy level exists or not. So this is 5, this is 3, so 8, 10, 11. Okay, so this energy level has an energy of 11 electron volt. So the electron would jump to this energy level here. Okay, let's draw that transition. So the electron jumps to the energy level with energy 11 electron volt. So electron is here now. Okay, the electron is at the outermost shell. What if you increase the energy of the incoming photon further? So now I'm replacing the visible light source with a UV source. Okay, let's go back. So we have a UV source. ultraviolet source. UV photons have energy higher than that of visible light source. So let's say this UV photon has an energy of 15 electron volt. This photon would interact with the electron would absorb the photon. So if you have 11 electron volt, you can reach the outermost shell. If you have more than electron volt, you are basically out of the atom, right? So this photon is supplying an energy of 15 electron volt. Using that energy, electron would jump out of this metal. So electron is out of the metal now. We call it photoelectron. Oh, we just learned a name for this effect, photoelectric effect, right? If you expose a metal to an electromagnetic radiation of sufficient energy, it could kick the electron out of the metal. This effect is called photoelectric effect.